Hello, welcome. I am Lumala Goodwill. Today I'm going to take you through magnetic effect of an electric current. This is a topic continuation from magnetism. Here we are going to look of how a conductor carrying current placed on a magnetic field is affected. And we are going to look at some of the application of magnetic effect of an electric current, which includes like electric motors, and we will see how the science behind their operation. In these diagrams you can see the first one is an electric bell, and for an electric bell we are going to learn how it functions. It is normally found in schools. This is what keeps you alerts you when the time is and when the class time starts and when the class time ends, time for lunch, time for games, time for preps. And the second one is an electric motor. This is a commercial electric motor. In this topic we are going to learn about how a simple DC electric motor works. This one is an AC motor. Keep in mind there are two types of current. There is an AC one and there is a DC current. DC means direct current while AC means alternating currents. The last one is a circuit breaker. The circuit breaker normally found on meter box. You can see it in schools, at homes, workplace. The circuit breaker, which helps in cutting off high current unwanted current frequencies. Normally it is used in meter box. A meter box normally contain AC current, hence a circuit breaker may contain AC current. As you can see, it is rated 220 volts, which is normal voltage rate for most of household, and it is around 32 watts. It normally helps your devices from spoiling and also helps in short circuiting. In our lesson, we are going the lesson objective for our class today there is by the end of the lesson you should be able to state the principles related to the magnetic effect of an electric current, perform and describe an experiment to determine the direction of a magnetic field around a current carrying conductor, determine the magnetic field patterns on a straight conductors and solenoid, construct a simple electromagnet, explain the working of an electric bell, magnetic relay system and circuit breaker, experimentally determine the direction of a force on a conductor carrying current in a magnetic field, and state and explain factors affecting force on a current carrying conductor in a magnetic field. And the last one is to explain the working of electric motors. There are others like the working of the working of moving coil microphone and moving coil loudspeakers, but for today class we only tackle these ones. We'll start by Hans Christian Ørsted. Have you heard of the person? This is a man, a scientist in 1819 who discovered that a conductor carrying current has a magnetic field around it. Apart from Hans Christian Ørsted, there are other scientists that have contributed in the research of magnetic effect of an electric current. This include like Michael Faraday, like Fleming's, like Maxwell's, who came up with the Maxwell's corkscrew rule, and like others who came up like the swimming rule, the Ampere swimming rule. He observed the direction of a compass needle when the current was switched off. The direction depends on whether on two factors: whether the compass needle is above or below the conductor, or the direction of current in the conductor. This is whether the compass is placed above the conductor may be different. The alignment of the needle will be different when in the below the conductor. And about the direction of current, when current is moving forward, the needle will point on different direction as the current is moving backwards. To determine the direction of the compass needle, we'll use the Ampere's swimming rule, which says that imagine you are swimming along the wire in the direction of current and you are facing the compass needle. The north pole of the needle will turn towards your left. As in the picture, you can see the swimmer is swimming forward. The arrow shows the direction of current, and this is the compass needle. The compass needle is here, and its north pole is here, and the other end is the south pole. The left hand and the right hand are here. So when the person is swimming in the direction of current, the left hand is being the magnetic needle is shifted towards the swimmer's left hand, and the south pole is around here. This is just in relationship, is according to the Ampere's swimming rule. The direction of compass needle we say the direction of compass needle depends on two factors. First one was whether was in the direction of current and whether the compass needle is above or below. We can say, to shorten thing, we can say the orientation of the compass needle. This is whether it is above the conductor or below the conductor. Here we have two photos, and the first one majorly describe the compass needles above the wire, and the second one compass needle below the wire. In the pictures, you can see the direction of current. Here is moving up, here is moving down, here is moving up, here is moving down, and the compass needle is this one. The shaded part is the north, and the unshaded one is the south. Here is the north, south, north, south, north, south. So in this scenario, the compass needle is facing this direction and current is facing. And so you can see when we are moving towards, we are moving along. We can take a scenario like a person swimming. As we said, the compass needle is above the wire. A person swimming above the wire. Here we mean a person swimming facing upwards in the sky, swimming along the wire, along the compass, along the current, moving with current in the same direction. Hence, the compass needle will be, the left hand of this person will be towards this side, and the right hand will be towards this side. The second scenario, current is moving downwards. Hence, the person swimming facing upwards, moving downwards, his left hand will be towards this side, while right hand will be toward this side. In the second picture, current is moving upwards, but the difference is the compass needle is below the wire. So we can take a scenario as a swimmer swimming while facing downwards. Hence, while moving upwards, his left hand will be towards this side, and while moving downwards, his left hand will be towards this side. Hence, we are moving to magnetic field patterns. We'll be looking at magnetic field patterns in two scenarios, in a straight conductor and in a solenoid. A straight conductor is such as a straight up a straight wire, e.g. a straight wire, something that is straight, and a solenoid is something that is coiled, either coiled in a coil like an iron core or just coiled, looking like a spring. Here we have a EMF source, which is a DC one having a positive terminal and negative terminal. Current is moving from the positive terminal to the negative terminal. Keep in mind that current and electrons move in opposite direction. As in this scenario, electron will be moving from negative terminal to the positive terminal. Here is a rheostat. The main function is to control the amount of current. Here is an ammeter. An ammeter here is to measure the amount of current. This control, this measures the connecting wires, which are conductors of electricity. This allows the current to pass freely from one terminal of the battery to another. So come here, the black dots are iron filings. Here it's a compass needle, and the circles are the magnetic field patterns. And a conductor carrying current is made to pass straight vertically through a sheet of cardboard. Like here, the conductor is passing vertically, and the sheet and the cardboard, it is at 90 degrees to the conductor. And some iron filings are sprinkled the cardboard like here. The iron filings settle in centric circles. The essence of using iron filings in this scenario is that iron filings are ferromagnetic materials. In this, I mean that iron filings are good, they're easily magnetized and easily demagnetized. Hence, the essence of using a material that easily magnetized in this scenario is that as the current passes through, the iron filings will be easily magnetized, and they will follow the path of magnetic field patterns. When a compass needle is used instead of iron filings, the compass needle is aligned in circles pointing in clockwise direction. When current is reversed, the needle points in anti-clockwise direction. When current is moving downwards, the needle is in different direction as compared to current moving upwards. The direction in which the needle faces is the direction of the magnetic field due to that conductor. The direction can be determined by right-hand grip rule, which says that if a conductor carrying current is gripped in the right hand with the thumb pointing in the direction of flow of current, the first finger will point in the direction of magnetic field. As you can see, this is the right hand of a person, and is the thumb pointing upwards, meaning current is moving from downwards to upwards. Hence, magnetic field is moving in this direction. As in a scenario, you can be given a question with the movement, the arrow showing the motion of magnetic field, and can be asked the direction of current. Hence, by using the right hand grip rule, which says that if the thumb is moving in the direction of current, you can easily use your right hand to determine the direction of current on that conductor. In the next video we'll see how magnetic field appear experimentally.
I have a piece of plastic through which I've drilled a hole, and then I took a wire and looped it through the hole 10 times. So I have 10 strands of the wire here flowing through this hole. So if I have 1 amp of current flowing in the wire, I will have essentially 10 amps that's flowing in a straight line through the hole in the plastic. I'm now going to sprinkle some iron filings onto the plastic. I will now apply a current, and I will have to tap the plastic to get the iron filings to move. And you can see how the iron filings have rotated to form circles around the wire, indicating the form of the magnetic field intensity generated by a current carrying wire.
As you have seen how magnetic field patterns may look in an experiment. Now we are going to look at magnetic field due to a solenoid. The previous one was due to a straight current carrying conductor. Here, what is a solenoid? A solenoid is just a wire that is coiled, may have a core or may not. A solenoid is a serial coil of wire acting as an electromagnet when carrying electric current. Have you ever seen? The direction of magnetic field can be determined by right-hand grip rule, which states that if a conductor carrying current is gripped in the right hand of the thumb, pointing in the direction of the flow of current, the first finger will point in the direction of magnetic field. It's when you place your right hand like this. If a conductor carrying current is gripped in the right hand, with the thumb pointing the direction of the flow of current, the first finger will be pointing the direction of magnetic field. To produce stronger magnets, coils are wound on a soft iron core. This is a picture representation of a solenoid, and here we have wires wounded, and this direction of current may be from here to here, and these are magnetic field patterns. The direction of current and polarity is a solenoid. Direction of current and magnetic field in a solenoid can be determined by the second right hand rule. The previous was the right hand grip rule, and this is the second right hand rule, which says that the thumb of the right hand, the thumb to the north pole of the solenoid. The thumb, when the thumb is pointed to the north pole of the solenoid, when the hand is wrapped in the same way as the electric current around the solenoid, meaning when the thumb is pointing to the north pole like this, the remaining fingers points to the direction of current. Hence, in this picture, current is moving downwards. In this video, we are going to see how polarities of how to determine the direction of current. As you can see, current is moving in that direction. This is the north pole and the south pole. hope you have understood how to determine the polarities. This is the North Pole, South Pole in a solenoid and the direction of current. Just when current is maybe is moving like this, the North Pole may be in the other side. This is not in construct with the polarities of the EMF source. Factors affecting the strength of an electromagnet. There are four factors that may affect the strength of an electromagnet. And the first one is amount of current. The more the current, the stronger the electromagnet. When you increase the current of the source, maybe you are using one battery and you increase to 3. So in order to achieve more strong electromagnets, you need to increase the amount of current. The amount of current may be increased by increasing the batteries or increasing, or if you are using a rheostat to control power, you may turn it to in order to get a lot of current. Hence, the number of turns of wire in a solenoid. The more the number of turns, the stronger the electromagnet. By making more turns, the surface area may increase. Hence, this electromagnet may be more strong. The shape of the core. A U-shaped core will produce stronger magnetic field than a bar core. A U-shaped may be like this. This is the U-shaped core, and the bar core is just a straight one. The explanation for this is that in a U-shaped core, the polarities, the North Pole and the South Pole, are close together, hence making the magnet more stronger than the bar core, where the polarities are far end from each other, making the U-shaped more stronger. The length of the solenoid. The smaller the core, the stronger the electromagnet. When you use a smaller core, a shorter one, the electromagnet will be more stronger than using a very large one. This may make it weak. Hence, the length of the core is inversely proportional to the number of the wires in the solenoid. Application of electromagnet. We will be looking at 3 applications of electromagnet. First is the electric bell, electric circuit breakers, magnetic relay system. As at the start of the lesson, I introduced an electric bell and circuit breakers. What is an electric bell? In an electric bell, as we have here a sample of an electric bell, this is a switch battery or an EMF source. This is an electromagnet. As you can see, wires wound inside a core. This is a soft iron core. This is the North Pole, and this is the South Pole. As a right-hand rule, the North Pole and the South Pole, it is more easier to find the direction of current. Hence, you can tell, if you have not given the polarities of the magnet in a question of the EMF source, you can easily get them. This is a spring. This is a soft iron armature, a gong, and a hammer. I'm going to explain the function of each part of the electric bell, and their parts and their function in an electric bell. The first one is an electromagnet. When the electric current flows through the coil of wire, it becomes magnetized, attracting the armature. The armature is made of a magnetic material. Hence, when the electric current flows through the coil, it becomes magnetized. There is a reason for using an electromagnet over a permanent magnet, because in this, a bell rings in a certain frequency. To achieve a certain frequency, the electromagnet must be magnetized and demagnetized at very slow, at a certain frequency in order the bell to ring. An armature. This is a piece of iron or steel that is attracted to the electromagnet when becomes magnetized. A spring is connected to the armature. When electromagnet is not energized, the spring pulls the armature away. Gong is a metal cap or bell that produces the ringing sound when struck. So the hammer is the one that strikes the gong. The gong is something that looks like a plate or a cup that when it's being hit, the sound comes out. That is the sound that the bell produces. These are usually attached to the armature. When mixed with the gong, sound is produced. So this hammer make contact with the gong when the armature is attracted to the electromagnet circuit. These include a power source, battery, or like electricity, maybe DC or AC. Wires, these are conductors, and a which can turn power on and off. When the switch is closed, the current flows through the electromagnet, causing a bell to ring. So the electromagnet may be connected to, instead of a switch, may be connected to an alarm system or another source of power. How it works. This is the working principle of an electric bell. When the switch is closed, current flows through the circuit and the core becomes magnetized. This is the reason why the electromagnets are used instead of permanent magnets, because when current flows, the electromagnet becomes magnetized. Hence, the electromagnet induces magnetism to the soft iron armature, which is then attracted to the soft iron electromagnet. The hammer attached to the armature strikes the gong. The attraction to the soft armature separates the contacts, breaking the circuits. The magnetism in the core therefore dies, and the spring returns to its original position. Contact is made again. The process is repeated, meaning this means that the attraction of the soft armature separates the contacts. When you separate the contact, current breaks. Hence, electromagnet become magnetized because it depends on the current in order to be magnetized. Because it is demagnetized, the armature is no longer being attracted, so it will be returned to its original position. Hence, due to this repeated action in some frequency, you may hear the bell ringing. In this video, we're going to see how electromagnets work.
An electric bell is a very simple electric device that consists of a power source, a switch, an interrupter, a soft iron strip with a hammer at its end, an electromagnet, and a metal gong. Let us see in slow motion how the electric bell works. When the switch is turned on, the circuit is completed and electricity flows through the electromagnet. The electromagnet attracts the soft iron strip and the hammer strikes the gong. As soon as the soft iron strip gets attracted to the electromagnet, it no longer touches the interrupter and the circuit is broken. When the circuit breaks, there is no current through the coil and the electromagnet can no longer attract the soft iron strip. The spring-loaded strip goes back to its initial position. As the soft iron strip again makes contact with the interrupter, the circuit is again completed and the same steps go on and on as long as the switch is on.
Hope this video has made you understand more about electromagnets. The second application of electromagnets is a circuit breaker. A circuit breaker is a magnetic device that breaks the circuit through an electromagnet when a certain amount of current is exceeded, or when a circuit is short-circuited. This means that when positive and negative terminal they are attracted, or in DC current, or in AC when live and neutrals comes together. The circuit breaker then breaks the circuit. It protects electric components from excessive flow of current. When excess current flows through the circuit, increased magnetic power of the electromagnet opens the switch, stopping electric current flow. Once the problem causing the excessive current flow has been corrected, the switch is closed by mechanical means. This is a diagram representation of an circuit breaker. As you can see, here is cable, terminal, contact, operating handle that enables you to switch back it on when the problem is solved. This coil assembly method, thermal element, cable, terminal. So the current may pass from here to here. This is load, this is input, and this is load current where electric components are. This is rail mounting, where it will be mounted on. This is a 3D representation of an circuit breaker, but this is a real circuit breaker, how it looks like inside. So the arc chamber is here. Here are the terminals in and out by metallic strip. Due to excessive heatage, excessive current makes them by the metallic strip heat. Hence, due to when it curves, it may switch power off. Circuit breaker have an advantage over fuse because when the problem is rectified manually, when it's manually turned on, while a fuse will need another new fuse for replacement. Also, circuit breakers are more better than fuses. They may be more faster, and this may help more than this. The diagram, the next video will help you to understand more about circuit breakers.
A tiny, interesting device called an MCB protects you and your house from electrical mishaps. This breaker saves you from two situations. First, short circuit, and second, overload conditions. In a short circuit scenario, the MCB trips in less than 3 milliseconds and isolates the internal connections. Let's see how this smart device detects current chaos so quickly and precisely. A simple device called a fuse, which has a low melting point wire, was used for home protection in earlier days. In both the fault conditions mentioned previously, the current spikes up, resulting in overheating and fusing the wire or breaking the circuit. However, every time the fuse would blow, you had to manually replace it. Until you could do that, good luck with the blackout. This commonly occurring situation is why circuit breakers were invented. The circuit breaker is an automatic on-off mechanism that keeps one side of the wire moving and the other fixed. During an electric fault, if the circuit opens wide, we are done with the MCB design. After the fault ends, simply manually turn it on. Before getting more into the MCB design, a small note about the current direction. An MCB gets activated in less than 3 milliseconds, which is way lower than the half cycle time period of an alternating current. So it is okay to show the current flow in a single direction throughout the analysis. Now the question is, how does this system recognize the occurrence of an electric fault? The answer is that it has sensing elements which activates a triggering mechanism. Let's first see how we can design a super quick triggering mechanism which opens wide. A clever mechanism to achieve this objective is shown here. This mechanism has a lever to which a rectangular ring is connected, as shown. The rectangular ring is connected by 2 springs and a central lever. In this position, both the springs are in a neutral state. When the lever moves up, the bottom spring compresses and the top spring expands. The forces of both these springs are eventually transferred to the lever via the rectangular ring, and this force will be in the upward direction. As you can see, the rectangular ring is initially at a negative offset to the center of the lever. The torque produced by the force acting on the rectangular ring will be in the clockwise direction. If you release the lever in this position, this clockwise torque will bring the lever back to its initial position. However, if you push the lever farther up, do you notice anything peculiar about the offset distance? It suddenly becomes positive, which means that after a critical limit, the torque will act on it in a counterclockwise direction. When the MCB is on, this will be the position of the lever. The structure of the MCB will block the lever from rotating further counterclockwise. Now, if an external trigger turns the lever slightly, the torque on the lever suddenly becomes clockwise and the circuit opens wide quickly without the need of an external force. Here, as the operator pushes the lever down, you can see in ultra-slow motion how the mechanism operates in practice. After a small angle, the lever generates its own torque and then there is no need to apply external force. Now, the only question
The magnetic relay system. So what is a magnetic relay system? A relay is an electromagnetic switch device that uses small current in another circuit, in an adjacent circuit. When the circuit is closed, current flows through the solenoid and the soft iron core gets magnetized. It attracts the soft armature and hence contact closes. This completes the circuit of heavy current in the motor. This is a video representation of how a magnetic relay system works.
In this video, you will learn about working principle of an electromagnetic relay. This is a small typical electromagnetic relay which is most commonly used in many applications. The main components of the relay are an electromagnetic coil, an armature, a spring system, a yoke, and fixed and movable electrical contacts. In electromagnetic coil, a coil of wire is wound on a soft iron core. It is used to generate the magnetic field to the soft iron core. The yoke is used to provide a low reluctance path for the magnetic flux produced by coil. The movable iron armature is hinged to the yoke with spring arrangement. One or more sets of moving electrical contacts are mechanically linked with the movable iron armature. Due to this arrangement, when the relay is in de-energized condition, there is an air gap between the armature plate and core. In this condition, some of contacts would be in closed condition. These contacts are called as normally closed contacts or NC contacts. And some other contacts would be in open condition and they are called as normally open contacts or NO contacts. Note, the type of contacts NO and NC are described with respect to the de-energized state of the relay. When supply is provided to electromagnetic coil, it generates a magnetic field. So the armature is attracted towards the electromagnet core. The consequent movement of the movable electrical contacts break the NC contact connection and they move to open condition. Simultaneously, the NO contacts move and their contacts get to closed condition. When the current flowing the electromagnetic coil is switched off, the relay coil gets de-energized. Then the armature is returned to its original position by the spring arrangement. Hence, it restores the contacts to the normal condition with NO contacts open and NC contact close. Now you have learnt about working principle of an electromagnetic relay.
Hope you have understood. So in today's class, we have learned about the magnetic effect of an electric current, and so far we have able to pass to understand the laws relating to the magnetic effect of an electric current, like the Ampere swimming rule and how they works. And also we have got to learn about magnetic effect, the magnetism in straight conductors and also in solenoids. And so far we have learned the application of electromagnets like magnetic relay systems, circuit breakers, and electric bells. In our next class, we will be passing through forces on a current carrying conductor, and we will see how amount of current and magnetic field strength affect force in a wire in placed in a magnetic field in the magnet, and a force acts on the wire when it's placed in the magnetic field, and the magnet of the force depends. So the magnet of the force depends on the amount of current and the magnetic field. Also, we'll be able to look at the Fleming's right hand rule. Later on, we'll be looking at motors, how motors works. Thank you.
We have
Then
studied that an
yeah.
electric current carrying conductor produces a magnetic field.